A relation R on a set A is reflexive if every element of A is related to itself. For all in A, the ordered pair of comma is in R's. Think of a friendship network where every person automatically likes themselves. The likes relation is reflexive because you always like yourself. Example, let A equal the set 1, 2, 3 and define R equals the set of pairs 1, 1, 2, 2, 3, 3, and 1, 2. Because each ordered pair of comma A for in A appears, R is reflexive, even though it also contains an extra pair 1, 2. A relation R on a set A is symmetric if whenever an element A is related to B, then B is also related to A. For all in B and A, the pair A comma B is in R implies the pair B comma A is in R's. An everyday analogy is a two-way road. If you can drive from city X to city Y, you can also drive back from Y to X. Example, let A be the set red and blue, and let R be the set of ordered pairs red, blue, blue, red, red, and blue, blue. Since every pair appears with its reverse, R is symmetric. A relation R on a set A is transitive if a chain of two related pairs can be skipped in one step. Formally, for all of B, C, and A comma B is in R and B comma C is in R implies a comma C is in R. Imagine D is an ancestor of relation. If Alice is an ancestor of Bob and Bob is an ancestor of Carol, then Alice is automatically an ancestor of Carol. Example, let A equals open brace 1, 2, 3 close brace and R equals open brace open parenthesis 1, 2 close parenthesis, open parenthesis 2, 3 close parenthesis, open parenthesis 1, 3 close parenthesis close brace. Because 1, 2, and 2, 3 imply 1, 3, which is present, R is transitive. An equivalence relation on a set A is a relation that is simultaneously reflexive, symmetric, and transitive. It groups elements into chunks called equivalence classes, where every member is indistinguishable under the relation. Real-world analogy has the same birthday as among people. Everyone shares that birthday with themselves, which is reflexive. If Alice shares a birthday with Bob, then Bob shares it with Alice, which is symmetric. If Alice shares a birthday with Bob and Bob with Charlie, then Alice shares it with Charlie, which is transitive. Formal example. On the set of integers, define a related to B if and only if a minus B is divisible by 5. This relation is reflexive because a minus A equals 0. It is symmetric because if a minus B is a multiple of 5, then B minus A is its negative, which is also a multiple of 5. It is transitive because if a minus B and B minus C are multiples of 5, then a minus C equals a minus B plus B minus C, which is also a multiple of 5. The equivalence classes are the residue classes modulo 5. The class containing 0 includes minus 10, minus 5, 0, 5, 10. The class containing 1 includes minus 9, minus 4, 1, 6, and so on. Reflexivity test. For each in A, verify a comma A is in R if any self-pair is missing. R is not reflexive. Symmetry test. For each A comma B is in R, check that B comma A is in R. It is enough to scan the list once. The moment a counterexample is found, symmetry fails. Transitivity test. For each pair A comma B is in R and each B comma C is in R. Look for a comma C in R. This can be done by constructing a lookup table, for example a hash set for constant time membership test, then iterating over all middle elements B. Early exit. If any test fails, stop. The relation does not have that property. Complexity note, reflexivity big O of A, symmetry big O of R, transitivity big O of A times R in the naive approach, but can be reduced with matrix multiplication Warshaw's algorithm to big O of A cubed for dense relations. The checklist gives a systematic way to answer is R reflexive, symmetric, transitive for any given finite relation. Explanation: counterexample constructions. Not reflexive. Let A be the set 1, 2, 3 and R be the set containing the pairs 1, 1 and 2, 2. The element 3 lacks 3, 3, so R fails reflexivity. Not symmetric. Let A be the set O and B and R be the set containing the pairs A B, A, and B be the pair A B is present but B O is missing, breaking symmetry. Not transitive. Let A be the set 0, 1, 2 and R be the set containing the pairs 0, 1 and 1, 2. Here 0, 1 and 1, 2 are in R but 0, 2 is not, so transitivity is violated. These tiny examples make it easy to see which property fails by inspection. Explanation. When we compose two relations R subset of across B and S subset of B cross C, the composition S circle R equals the set of pairs A comma C such that there exists B in B with A comma B in R and B comma C in S. Preservation of transitivity. If R and S are both transitive and the middle set B equals A, so we are composing a relation with itself, then the composition need not be transitive. Example, let A equal the set 1, 2, 3, and define R equal the set of pairs 1, 2 and 2, 3. R is not transitive, missing 1, 3, but R circle R equals the set 1, 3, which is trivially transitive because it contains only one pair. Conversely, take R equal 1, 2 and 2, 1 on A equal 1, 2. R is symmetric but not transitive. R circle R equals 1, 1 and 2, 2 is reflexive and transitive, the identity relation. Thus, composition can create transitivity even when the original relations lack it, but it can also break it. Let R equal 1, 2 and 2, 3 and S equal 2, 1 and 3, 2. Both R and S are not transitive, and their composition S circle R equals 1, 1 and 2, 2 is transitive, showing that composition can both add and remove the property depending on the specific pairs. Typical exam problems. Prove or disprove that a given relation is an equivalence relation. Let R be defined on the integers by a relates to B if and only if the absolute value of A minus B is less than or equal to 2. Students must test reflexivity true, symmetry true, and transitivity false, because 0 relates to 2 and 2 relates to 4, but 0 does not relate to 4. Hence, R is not an equivalence relation. Construct the minimal closures. Reflexive closure of a relation R is R union, the set of ordered pairs A comma A for all in A. Symmetric closure is R union, the set of ordered pairs B comma A for all A comma B in R. Transitive closure can be obtained via Warshall's algorithm or by repeatedly adding A comma C whenever A comma B and B comma C are present. Given A equals the set of 1, 2, 3 and R equals the set of ordered pairs 1, 2 and 2, 3. Ask for the reflexive symmetric transitive equivalence closure. Add missing reflexive pairs 1, 1, 2, 2, 3, 3. Add symmetric pairs 2, 1 and 3, 2. Then compute transitive closure, eventually obtain the full relation of I, j for all I, j in A, that is the universal relation on A. These types of questions test understanding of the definitions and the ability to manipulate relations algorithmically.